This is the first video in the differential equations unit. I plan on doing 1 page per video just to keep the videos at a reasonable length. So let's go ahead and jump right into it. First question, what constitutes a differential equation? And pretty much it's exactly the way that sounds. It's an equation that has a derivative in it. Okay? So a differential equation can be thought of as just an equation with derivatives in it. Maybe a little simplistic, but that pretty much sums it up. So for example, if I said f prime of x equals 5x plus 1, this is a differential. Usually you're not going to see them with f primes. Usually it would be written as something more like dy dx equals x cubed. Something a little more complicated might be 3y dy dx minus 4 equals 2x plus dy dx. So again, an equation has the equal sign, and we've got derivatives in it. Sometimes it's just on one side, sometimes it's on both sides. Now, the question is, how do we solve a differential equation? Well, basically, it's if we have a derivative, we're trying to figure out where it came from. We're trying to figure out the original equation or the original function, as it is quite often. So what we're going to do is we will anti-derive both sides of the equation. That is to take the indefinite integral of both sides, giving us the original function. So for example, if I gave you this differential equation, dy dx equals negative cosecant squared of x plus 2x minus 5, we would go ahead and take the indefinite integral of both sides. Okay. We can go ahead and multiply by dx here. That'll take care of that on the bottom. So the integral of dy is y. And the integral of negative cosecant squared of x is going to be the cotangent of x plus the antiderivative of 2x is x squared. The antiderivative of negative 5 or minus 5 is going to be minus 5x. And of course, as always, when we take the indefinite integral, we need that plus c value. And that plus c really is the answer to this next question. What's the difference between a general solution and a particular solution? Well, a general solution is going to be a solution that technically has infinitely many values or infinitely many answers, because there are so many functions or infinitely many functions where we could have a constant on the end of it that when you derive just becomes 0. So the difference between a general solution and a particular solution is the general solution is going to have the plus c on it. The particular solution, we're going to use an initial condition that you'll be given in the problem to find that value of c. And then we're going to substitute that value in. So for example, in this next one, it says find the particular solution of the differential equation. Up here, we just found a general solution. That's why we have the plus c. Now we're going to start with the plus c, but we'll use this initial condition to find out what that value of c is. So we're going to go ahead and we'll just integrate both sides. So the integral of the left side gives me y. The integral of the right side, the antiderivative of e to the x is e to the x minus, and the antiderivative of 6x squared is going to be, 2x cubed plus c. Now I'm going to let my x go to 1. My y go to 0. So I end up getting 0 equals e to the 1 minus 2 times 1 cubed plus c. So let's go ahead and calculate that. E to the 1 is e. 1 cubed is 1 times 2 is 2 plus c. So we'll go ahead and we'll add 2 and subtract e so that I isolate the c. So when we add 2 and subtract e, I get c is equal to 2 minus e. So our particular solution for this is going to be y equals e to the x minus 2x cubed plus 2 minus e. Now, quite often when you're doing these, it's going to ask you to find the domain of this function. Now, in this case here, the domain would be all real numbers, and that's fine. But quite often, the domain we're going to have to restrict. We're going to have to decide on a particular open interval over which we define that function. And the reason it matters The reason it matters is, let's again go back to this. We have the derivative. So we're trying to find a function that is differentiable. And we know that if a function is differentiable, then it must be continuous. So if a function is differentiable, then it must be continuous. So there are times that when we go to and integrate and we find a particular solution, that function just inherently has discontinuities. So we're going to have to find the part of the function that contains the initial condition and isolate that section as the piece of the function we want. So we'll be restricting the domain of the function to satisfy the initial condition. And here's an example of that, number 3. To find the particular solution of dy dx equals secant squared, whose graph passes through the point 0, 3, state the domain of the solution. So again, we're going to just start off by integrating both sides. So I get y is equal to the antiderivative of secant squared is the tangent of x plus c. Let's substitute in 0 for x, 3 for y. Tangent of 0 is 0, plus c is c. So my particular solution is y is equal to the tangent of x plus 3. Now let's go ahead and take a look at what this graph looks like. Well, that means we're going to take the graph of the tangent of x, which has vertical asymptotes at negative pi over 2, as well as out at 3 pi over 2 and negative 3 pi over 2. And normally it goes through the origin. So we have these vertical asymptotes here, which again are just a form of discontinuity. And normally the tangent graph comes up, passes through the origin, and will continue up. But that entire graph has been shifted up 3. So our graph is going to come up, go through 0, 3 before going on up again. And it's going to do the same thing on every one of these little intervals here. And it would continue to do it out here, and it would continue to be out here. Now we have infinitely many little pieces of this, but only one of these pieces contains the given point 0, 3, and that's this piece right here. So the domain that we want is the domain that includes the interval negative pi over 2 less than x less than pi over 2. And that would be the domain of the solution. And that's page 1.